Okay, well, thank you for having me. Appreciate being invited. After the recent political things, I saw Lee Greenwood was singing that song, God Bless the USA, that he sings all the time. Been doing it for years. And someone asked him, don't you ever get tired of singing that song? He said, never. He will always sing it. He'll always want to sing it. So I feel the same way about fusion. I enjoy talking about fusion, especially to people who don't really know about fusion, to get them understanding it, because this is the way to get people to accept a new energy source that sometimes they're a little reluctant when they hear the word nuclear. So really enjoying doing this and appreciate the opportunity. I guess do I control the slides? Julie does. Oh boy. Okay, Julie.
Be careful, Fred.
Next slide. There we go. So I know you people don't understand what nuclear energy is. So that's nothing new. I want to tell you just a little different perspective on it. Hopefully it'll be kind of enlightening. So I want to start with what's nuclear energy. What is nuclear fusion then? So what's special about nuclear fusion? Why do we care? Who cares if we have another power source? And then at the end, kind of what does a fusion machine look like? Just so people get a perspective. And what you'll find the answer is, just like if asked 40 different people, you get 40 different fusion machines. So there is no fusion machine like a nuclear reactor. The current reactors, everyone knows what one looks like. Fusion machines you'll find are different. But we'll talk a little bit about that and finish up with the future of fusion, where we are now in the industry, what it's looking like going forward. And Julie is right on top of things. So let's start with nuclear energy. Everyone's seen this. This is an atom. Okay, all the matter, all the mass, the universe is made up of atoms. The key thing here is that I want to address is the nucleus. Of course, you're women in nuclear, you know the term nuclear energy comes from the nucleus. So they have a nucleus of an atom. It's got neutrons and protons. This will become important later, so take notes. Protons are positively charged. Neutrons are just neutral. But the point here is that the mass of the neutron and the mass of the proton are about 2,000 times the mass of the electrons that are floating around outside. So that's key, because what we said is all the matter in the universe is made up of atoms. All the mass of the atom is in the nucleus. So all the mass of the universe is in nuclei of atoms. Okay, that's kind of mind-boggling a little bit, but if you think about it, it makes sense. So, who cares? Well, this guy with the wavy hair years ago came up with this expression, E equals MC squared, which I think everyone has heard about. So that's a nice equation. He was a patent clerk in Switzerland when he came up with this, and I guess he just thought about these things at night. But the point of this equation is that energy and mass are the same thing. And you can take many, many courses on energy and mass because they're equivalent. We're not going to cover that here, but just keep that in mind. Energy and mass are the same. That's what the equation says. So he said, if I have mass, I can convert that to energy. If I have energy, I can convert that to mass. Now, you got to be thinking on the nuclear level. On our classical sense here in a room like this, you can't do that. But at the subatomic level, energy and mass are equivalent. So again, the question is, who cares? Let me give you a little different perspective on this. So if I had a particle of sand, and I could convert all the mass of that particle of sand to energy, you can't do that, but the way this equation works, if I can convert all that mass to energy, the mass of that particle of sand is equivalent to 1 ton of TNT. Okay? A lot of energy in the nuclei, in the nucleus. If I have a penny, if I can convert the mass of the penny to electrical energy directly, I could power New York City for over 2 years. So I think that gives you just a little different perspective on nuclear energy and what this equation means. of the energy that's actually contained in the nuclei of atoms. Pretty interesting perspective, I thought, when I was doing this. Okay, so if we go to the next slide, how do we get that energy out of the nucleus? Okay, now we know, and the scientists, if you watch the movie Oppenheimer, the scientists back in the 30s and 40s understood this. They realized, wow, there's a lot of energy in this. And at the time, their thought was, how do I make a weapon out of all this energy? And that's what they did, and that's how nuclear energy was introduced. But the point was, they knew that there's a considerable amount of energy in these nuclei. And if I could just get a little piece of that energy out, I could create a lot of energy for use. So the first thing they came up with was fission. This is the easiest. That's what all the nuclear reactors now, the process used in the reactors is based on nuclear fission. And that's taking a heavy nucleus. In most of the cases, it's uranium. So a heavy nucleus. And the point is you can have a neutron wander by and get captured by the nucleus. Remember, the neutron is neutral charge, so it doesn't get affected by anything. It just meanders around. And it impacts a uranium nucleus. It'll fission. It can fission. Shouldn't say will. It can fission. When it fissions, it splits into two pieces, or three, or four. Multiple pieces. But generally, two is on average. It splits into two pieces and releases energy and gives off more neutrons. And the key thing why the equation E equals mc squared is important here is that the mass of the nuclides and the mass of the particles after the reaction is less than the mass of the particles before the reaction. And that's what's key, because now I've taken mass and I've changed it to energy. I've reduced the mass of a system. When you burn coal, burn oil, burn gas, the mass stays the same. It looks different, and it's gone off in gas, and it's gone off in different molecules. But if you captured everything, the mass is identical. Those are chemical reactions. In the nuclear reaction, you actually change the mass and release that little bit of that energy that was in the nucleus that we just talked about. And you can use that then for various purposes. So that's fission. That's what nuclear reactors work on now. So let's go to fusion. And now we talk about light isotopes, light atoms. Now this is hydrogen. It's got hydrogen comes in three flavors. You got if you want to be a nuclear physicist, you got to call it protium. Okay, you can't just call it hydrogen. That's protium, which is your general run-of-the-mill garden variety hydrogen. One proton is a nucleus, an electron zooming around. Then there's deuterium, which is a proton plus a neutron in the nucleus. That's naturally occurring. It's in water everywhere. Very small percentage in water, but still it's there in nature. And then there's tritium, which is one proton and two neutrons in the nucleus with one electron going around. So all hydrogen atoms have one proton in the nucleus. That's the key. That's how you know it's hydrogen. It's got one proton in the nucleus and then various number of neutrons in there. So I'm just introducing this as hydrogen. On the right is helium. That plays a role in fusion also. So that's two protons, two neutrons in the nucleus. Now it has two electrons in the outer shell. You have two protons in the nucleus to make that electrically neutral. So those are neutral atoms of hydrogen and helium. Isotope, the term isotope just means it's hydrogen because you have one proton, but different number of neutrons in the nucleus give you different isotopes. So we won't use that term, I don't think, much, but we'll see. So the point is, we've got different types of hydrogen, very light nuclei. So if we go to the next slide, let's see what fusion is. So instead of splitting a large nucleus into two or more pieces and releasing energy, you can actually combine lighter nuclei. In this case, I'll just stick with hydrogen, two types of hydrogen, deuterium and tritium. People are looking at other things, but that's the most common fuel they're looking at now. So if I'm able to combine deuterium and tritium and push them together, then I form helium and one neutron. So, and I can give you a whole nother lecture on why, in this case, the mass afterwards, after the reaction, is also less than the mass of the system beforehand. So if you take a nuclear physics class, you can learn that if I split heavy isotopes heavy atoms, I have reduced mass, or if I combine light atoms, I reduce mass. If I combine heavy atoms, I get increased mass. If I split a light atom, I get increased mass. Don't worry about that. Just take it for a fact that that's true. That's why you have fission on the heavy isotopes releasing energy. Fusion for the lighter isotopes releases energy. So Julie, if we go to the next slide. So why is this so hard? We talk about fission, no problem. The neutron, which is, like I said, neutral, wanders into the uranium, splits it. No big deal. Fusion, you have positively charged deuterium nucleus and a positively charged tritium nucleus. As you put those together, as you try to push those together, there's a force called Coulomb repulsion that tries to force them apart. Okay, force of nature, two like charges repel each other. So if you try to push these together, they want to go apart. They do not want to come together. So the trying to get them together is difficult, because you can tell by the equation. It's the only other equation in the talk, no more equations. E equals mc squared in this one, the only two. As r, the distance between the particles gets smaller, that force gets larger. Until when r is 0, that's an infinite force pushing it apart. Okay, that's pretty big force. So it's very difficult to get them together, and that's why fusion is such a challenge. So, but it's important. It's a really good form of energy. And again, if you watched Oppenheimer, if you saw that movie, there's a person called Dr. Teller, Edward Teller. As part of that movie, he was one of the characters. He was pushing Oppenheimer to develop the bomb based on fusion. He said, that's a bigger bomb. It's better. Let's work on it. Oppenheimer said, no, Ed, go in the corner. Matter of fact, he said, essentially, Ed, go in the corner. You work on it. We're all going to work on the fission bomb. And that actually kind of came out in the movie a little bit. But Ed Teller came up with this. He was working on that as a weapon while they're working on the fission bomb. So if we go to the next slide. So why do we care about fusion energy? It's the density of the energy in there. We talked about, a little bit of nuclear mass can give you a lot of energy. So this is a comparison of energy density of these fuels. So if you look on the left, you have 21,000 rail car loads of coal. And you can go across, you can read it. Is about a half ton of fuel, fusion fuel. That gives you the same energy out. So coal and oil, chemical reactions, it's burning, it's combustion, breaks up chemical bonds, releases energy. But fission and fusion on the right actually gets energy out of the nucleus. As we explained very early, a lot of energy in the nucleus. You get a little bit out, goes a long ways. So we want to go after fusion because it doesn't take a lot of fusion fuel to make a lot of energy. And if you go to the next slide, you'll see that first of all, you have an abundant fuel source for fusion. You need deuterium, which you get out of the water. We've been doing that for years. Savannah River site, we extracted deuterium from Savannah River for decades because the reactors used heavy water, what they call heavy water, which was deuterium oxide rather than hydrogen oxide, which is regular water. Canadians still making heavy water as we speak. They need them for their reactors. So get the deuterium out of the water. You have to make the tritium. Tritium is not naturally occurring. So you make that in the fusion reactor itself, and we'll talk a little bit about that. No high-level waste out of fusion. You get helium, what I show you, helium and a neutron. Helium's non-radioactive. You can blow up balloons with them. You can inhale it and talk like Donald Duck, and you can do all sorts of things with helium, but that's all it is. It's a regular helium that comes out. So no high-level waste. Those fission products I showed, when the fission splits into two pieces, those two pieces are what are the high-level waste. So you don't have that in fusion. No runaway reactions. If you saw the fission, which gives off another neutron or two neutrons or three neutrons, if it, the weapon, the nuclear weapon, that was a chain reaction that happened very quickly. You break you fission one nucleus, it sends out two or three neutrons. It's two or three more nuclei that spits out, 9 neutrons, and it just keeps on going. If you want to make a weapon, it goes very rapidly. So that's called a runaway reaction. In the current reactors, they don't have that situation. They don't have that geometry. But people worry about it, having runaway reactions, even though it's not really technically possible. and no long-term cooling. Most of the reactor accidents, there was only one that I know of that was a runaway reaction. That was back in the 50s. But the reaction, the ones in the Fukushima and TMI and Chernobyl, all had to do with cooling the reactor. It had nothing to do with the fission reaction itself. Because when you shut down a reactor, a nuclear reactor today, you still have to cool it. Because it's still generating heat. It's generating decay heat. All those fission products talked about, they're decaying, generating heat. You have to maintain cooling. You can't walk away and turn off the coolant too. So if you lose coolant, you can get melting. And on the right there, that's a picture of the core of Fukushima, considerable amount of melting. And that reactor shut down just fine, but they lost the cooling water pumps and the emergency backup power. So those cores melted on them. So advantage of fusion energy is you don't have any of those. So if you go to the next slide. So how does fusion exist? Told you have to get these particles together that don't like to react with each other. They want to repel. So if I just have a box of nuclei, a box of atoms, and this Brownian motion, if you remember back, maybe you had it or maybe you didn't have it, but that's just kind of random. But if I have a box of gas, the particles just randomly bounce around. If I heat it up, they go faster, but they still bounce around. They fill up the whole box. So that shows that box. So if I want to get them to react more often, and that's the secret of fusion, is you have to get them, if they keep bouncing off each other, eventually one or two will fuse and get together. So it's a probabilistic reaction. And that has to do with quantum mechanics. We won't get into that in this at all. But trust me, if you do it often enough, you will get them to react. So the point is to try to get all these nuclei bouncing off each other as fast and as long as possible to hopefully get enough fusion reactions to get useful power out. So I can increase the density of this gas by squeezing the box. Now they're closer together and more likely to interact. I can increase the temperature or energy. So I heat this up, they're bouncing around faster. So again, they collide more often. And I can do it for a long time. The longer they're in there, the more likely they are to react. So those are the three parameters I'm trying to increase density. Yeah, I tried to increase all those. I thought I had to decrease one. I'm trying to increase all those parameters, and that increases the likelihood of a fusion reactions to continue on. Getting fusion reactions, just so people know, because sometimes people don't understand, getting fusion reactions is not that big a deal. We've been doing it in universities for decades. Having fusion reactions is not the problem. The problem is getting enough of them for long enough time to get power out, to get more energy out than it takes to get the reaction to occur. So fusion reactions, if you want to be a purist, are no big deal. But getting enough of them is harder. So how do we know this works? Okay, we got a picture of the sun here. One way to get them close enough is have huge gravitational forces. Okay, we don't have those on Earth. You know, the sun, and I don't know the number, but sun is much higher gravity, squeezes those hydrogen. These are hydrogen-fueled fusion reactions in the sun. But the sun's been going on for a long time, and it's hot. It's like 15 million degrees centigrade. You'll learn a little bit later. That's not really hot, but it's hot enough. So, but the gravity is so great that it squeezes the hydrogen nuclei together, so and they react. And so, plus it's been there a long time. So you get a high density because of the gravity, reasonably high temperature, and you run this thing for billions of years. You know, you get a lot of power. You get a lot of energy out. So that's how the sun makes fusion reactions work. So go to the next slide. On Earth, we don't have that big gravitational force to squeeze those things together. So we have to use other forces that we have here. So let me introduce a concept of plasma, which you may or may not have heard of in the nuclear physics world, not the blood hospital type world. So plasma, and I find out now they teach this in 3rd or 4th grade. I never got it when I was 3rd or 4th grade. I was still eating crayons and licking paste. But they teach us now the plasma, which is essentially the fourth state of matter. So we think of solids, liquids, gases. If I have a solid and I heat it up, I get a liquid. If I heat up a liquid, I get a gas. If I heat up a gas, I get a plasma. And that means the electrons are now spinning around so fast around the nucleus, they finally just fly off into space. So now I'm left with a cloud of positive nuclei and a cloud of electrons, but they separate because there's so much energy in there, they don't combine into their normal mode of the electrons circling around the nucleus. So that's the fourth state of matter. So it's an ionized gas. Plasmas, you can see here, are like lightning. Lightning is a plasma. So you know about plasmas. Neon signs. I happen to pick a bar sign. I don't know why. But a neon sign is a plasma. You put electricity in either end, and you've got neon in there, or argon, or krypton, whatever color you want. And it energizes, strips the electrons off, and it emits colors. So those are plasmas in there. And why are plasmas important? Because plasmas can be controlled by magnetic fields. And we can create magnetic fields here on Earth. We can't have the gravity. We don't have gravity machines, but we can create magnetic fields, and we can create very strong magnetic fields. And the plasmas can be impacted by magnetic fields. So that's why the plasmas are important. Go to the next slide. Okay, here's another plasma experience that you all know about, northern lights. Okay, you get a solar flare, you get solar particles coming from the sun. That's a plasma. It comes in toward Earth. It interacts with our magnetic field. If you've seen pictures of magnetic field going from north to south pole that goes around the Earth. So the particles come in, the magnetic field shields the Earth. Otherwise, we'd get blasted by those particles. And they come in, they circle, they spiral around the magnetic field line. They go either north or south. And when they come in the north, they spiral around the magnetic field line, come down, interact with the atmosphere, and they slow down, giving off colors, giving off light, depending on what they're interacting with. We have nitrogen, carbon dioxide, all those. We have all the gases there in the atmosphere in different percentages. So when they interact and slow down, it gives off lights, and that's pretty. You also have those in the south because the southern, the particles go either way depending on how they're coming in from the sun. But that's, again, another example of a plasma that we're used to. Go to the next slide. So now we'll get into the fusion machine. What I'm going to show here is what I would call the most common form of fusion machine that's been worked on for 60 years. And in the red in the middle there, you have the plasma. So this plasma we talk about, you put in hydrogen and put in deuterium and tritium in there. You energize it so it strips off the electrons. So you have a toroidal tube, a torus, a donut. You know, physicists like to be fancy, so they call it torus. But inside this donut is a ionized gas. The metal surface on the outside is just steel. And I don't have a pointer or anything, but anyway, that gray torus is just metal. The red in the middle in the torus is your plasma going around inside. Then around outside, you got all sorts of magnets. Okay, if you look, you got toroidal field coils, a primary coil, poloidal field coils. Don't worry about any of that stuff. It's magnets, lots of magnets. And the point of the magnets are to do several things. One is keep it away from the surface, because if you have a plasma hitting the surface, it cools the plasma. And you don't want it. You want that plasma hot. It also doesn't do really well with the steel. It spits off that damages the steel if the plasma goes out there. So some of these magnetic coils are to keep it, just kind of constrict it and keep it inside the donut walls so they don't interact. Another one makes the plasma go around and around and around, so they collide. And another one will squeeze it so you increase the density of it. So the whole point is to contain that plasma, which is made up of deuterium and tritium nuclei, keep it away from the wall. Now this plasma, I talked about 15 million degrees sun. This plasma, they're trying to get at around 100 million degrees centigrade. So it's hotter than the sun. Has to be, because we don't have big gravitational forces to squeeze it together. So you have to increase the temperature. So that will be about 100 million degrees in the middle. And then that circulates it. So it runs around. You have 100 million degrees. They're bouncing around. And then you try to keep that going as long as you can. So the time element, we don't have the benefit of the sun, which is 4 billion years, but you try to keep it going for, hours to try to get energy out. So this particular magnetic confinement concept is called a tokamak. You may have heard of that. The Russians developed that in the 1960s, and that's just kind of stuck as a good way. And a lot of universities have these types of machines. So that's been studied the most, this type of thing. But the point is magnetic fields to constrict that plasma, heat it up, use magnetic fields to circulate it and make them collide as much as they can. So this is again, what I would say a typical fusion machine. Well, the next slide. Okay, so that's magnetic confinement. Another way to do it is called inertial confinement. Those are the two schools of thought right now, two sciences going on, are magnetic and inertial confinement. Inertial confinement, instead of having all these magnets and trying to squeeze this plasma, 100 million degrees, you take a really small, and I mean small, like a peppercorn or, that size sphere, you fill it with deuterium and tritium, and then you compress it as fast as you can. You squeeze it down. You do that with lasers, ion beams. I shouldn't say, there's someone that's using shock waves. Anything to try to squeeze that together suddenly, get that deuterium and tritium density increase so they react, and then it blows apart, and then hopefully you get more energy out of that than you put in. So that's inertial confinement. So those are the two primary fusion concepts that companies are working on now. So if you see that, see picture 3. So you start with number 1, you end up with 3. That thing's compressed way down, and then it gives off energy and fuses and blows apart. Go over the next slide. Okay, this slide shows experiments over the last many years. I talked about getting the density, temperature, and time up. So if you multiply those together, you get this y-axis, different stages, different values of that, temperature, time, and density product. At the very top, you have to try to get in that blue band up there. That's the whole goal. If you get up there, you'll have sustaining fusion. You'll have self-sustained fusion. It'll create enough energy to keep the fusion reactions going. So if you look at the years, I hope you can see that, I don't know. It's 1960, 1980, 2000, 2020 along the x-axis. And it shows various experiments internationally, which show over the years getting closer and closer and closer to that blue space up there. The one in the blue space, marked ITER, is projected. That hasn't happened yet, but the idea of the reactor they're building in France and have been building since 2010, the fusion machine in France, is to achieve conditions in that blue space. So we can see getting closer and closer and closer and closer, still not there. But now we're close enough where some companies and some places think they're going to get there. So a lot of the work has been done, and now they think they're almost there. Now they have better models, better computers, and they're demonstrating by models that they will get there when they build their machines. So there's a little leap of faith there as people are trying to get into that blue space. But you can see, what's going on over the last several decades of getting there. So if we go to the next slide, just yell at me if I'm going too long.
Oh, okay.
So this is the power. So what happens if you can get this? So we talked about the tokamak. You have the torus. Inside, you have the deuterium and tritium. We don't do that. Fluor doesn't do that. We don't care how they do that. That's these scientists and there are a bunch of companies that are doing that. We'll talk about that a little later. But essentially, you have this torus with the plasma in it. Around that shell, you will have what they call a blanket. I said deuterium you can get out of the oceans and the rivers and the lakes. Tritium you have to make. You cannot find tritium in nature. So if you have a neutron that goes into lithium, you have a neutron-lithium reaction which produces tritium. That's how we did the Savannah River for a long time. We made tritium for the weapons program. We had neutrons coming out of fission reactions and hit lithium rods and created tritium, take the rods someplace and melt them, get the tritium out. So that blanket is necessary to create the fuel for the fusion reactor. So you have to have that blanket. You can't go buy tritium down at Ace Hardware and supply your reactor. You have to make it. After that, it's just a standard thermal cycle. You have heat comes out of that blanket, convert it to steam generator turns a turbine. Turbine turns an electrical generator and you create electricity. So Fluor's part of fusion systems is really designing this outer part, designing the part to the left of the torus. But that's all the tokamak fusion power plant would look like. Fuse machine, create heat, generate steam, generate electricity. Okay, next slide. So here's I said we're going to talk about fusion machines a little bit. So here's something called a stellarator, which is like a tokamak, looks like a tokamak, but see all those little boxes, those little squares are on the outside. This company's decided to try to make all those things are magnets. Instead of those big magnets you saw on the tokamak, huge magnets that take up a lot of power, they've decided to try to make small, those things are, they say, like the size of an iPad. So you put all those around a torus, and then you can adjust the magnetic field in each of those to recreate what those big magnets used to do. So that's a stellarator, a little different shape, plasma. Don't worry about that. That's interesting. Then you have this mirror machine, another magnetic confinement concept. And this is you have a plasma in the middle there, that middle pink part, and the plasma goes back and forth. And if you pinch down the magnetic fields, you see where it gets narrow, the particles bounce back and forth. That's why it's called a mirror machine. Those are mirrors to particles. And so they go back and forth and hopefully collide and form more fusions. So that's why I'm saying these machines come in all sorts of, and there are 20 more designs I could have shown of people that have come up with their own types of magnetic systems. Each claim, and I've talked to a lot of these people, each claim there's the only one that's going to work. And each will tell you what's wrong with the other concepts and what's right there. So it's kind of a fun industry. JD likes to call it the Wild West. These are all still being developed, but they're getting closer and closer, which makes it fascinating. Go to the next slide. Okay, there is one technology that has demonstrated getting more energy out of a fusion reaction than goes in. I showed that picture of that curve, showing closer and closer and closer to that blue space. There actually is a company, or not a company, a laboratory that achieved getting fusion reactions in that blue space. And that was announced about 2 years ago. And that was the inertial confinement process I talked about. I said there's magnetic and inertial. So this is a picture this is at Lawrence Livermore National Ignition Facility. You see the person's finger and that little ball on top. That's the fuel pellet. That's what gets compressed. The cylinder in the middle is called the hull room. That pellet goes in the middle. That gets suspended in the middle of that. And then the laser beams come in through the ends of that hull room, through that hole, hit the inside of that inside surface of that cylinder, create a lot of X-rays. The X-rays then hit the pellet and compress the pellet. So the lasers don't actually hit the pellet, but they create an X-ray bath, which hits the pellet and compresses it. So if you go to the next slide. So this is interesting. So this is the fusion energy yields. They started these experiments in 2012. And on the bottom are the years. On the left is fusion energy out of the reaction. And they had experiments going, nothing. You can make the scale different, show something, but a little bit out. They put, by the way, just for reference, 2.2 megajoules. So 2.2 on the y-axis was the laser energy, was the energy going into the pellet, was 2.2 megajoules. So they would do this for what looks like 9-10 years. They were getting reactions, but not enough. All of a sudden in 2021, they got a significant reaction. They were changing the laser shape, the pulses, the pellets, you change all sorts of things and try it again. You change some more and try it again. You learn from that. So they kept optimizing the conditions. And then you notice 2022, 2023, now they're starting to get really close. 2023, that bar is December 2023. First time ever fusion reaction put out more energy. That looks like about a little over 3 megajoules came out of the reaction for 2.2 megajoules going in. Huge. I mean, that just made it across the world like instantly. Secretary of Energy had an announcement. It was just big to do. Huge breakthrough in fusion. And now you've seen since that time, I think they've done this successfully like 7 times. They keep changing, trying to get better. So sometimes they go the wrong way. Sometimes they get better. So you can see now they can reproduce that. So this is now a reproducible way to generate fusion energy, net fusion energy. The issue being that that's not a lot of energy. And so they need to get more and more and more because it takes a lot of power to power the lasers. So, but it's a breakthrough. It's a start. Go to the next slide. So the machine eventually will look something like this. It's just a big sphere. The pellet gets dropped down from the top, gets shot down from the top. The pellet is tracked by microwaves. When it's at the right place, the lasers go off, compress it, and that just keeps going. And it's like 10 times a second. So it's not like once a day or 10 times a second. Those things have to happen. Got a ways to go to get there. Right now they're doing 1 shot a month. So 10 times a second, a little bit of some technology has to be increased, but they have thoughts of how they're going to do that. So if we go to the next slide. First slide, this is another one. This is inertial confinement. I just put this in there for fun. It's called the Big Friendly Gun. But I talked about inertial fusion using laser beams. This is a UK company, and they shoot a projectile down this long tube and then they focus, creates a shock wave. You know, anytime you shoot a big particle down, you shoot a bullet, right in front of the bullet's a shock wave. So they shoot this thing down, a shock wave forms, and at the end there's a focus mechanism. It's patented that focuses the shock wave around the pellet. And then that's how they're going to do their inertial fusion. More power to them. If it works, great. I mean, 4 miles a second, 100-gram projectile. You know, but that's what I'm saying. It's fun. A lot of companies have their own ideas. I've talked to these guys at conferences, and they swear by it. They're making improvements. Next, Julie. I'm getting Lisa. Okay, we're getting near the end. So where are we in the fusion world? 45 companies have declared. So every once in a while, some new company will say, yep, we're here. So I don't think all the companies are actually making themselves known. A lot of them like to work below the radar. Brand new one came out a couple of months ago, September or so, Pacific Fusion or somebody. No one had ever heard of them. All of a sudden, someone gave them $900 million for their concept. So these people, so I'm saying 45 companies are out there that have their, I would say 43 different concepts. 4,000 employees in the industry right now, over $8 billion in private investment. So not getting a lot of government money, but the Jeff Bezos and Bill Gates and Sam Altmans and those people of the world are investing. So they do a survey every year, and they talk to these companies and say, when do you think fusion electricity will be delivered to the grid? And so half of them think 2031 to 2035. So in 5 to 10 years, half the fusion companies who are closest to reality half of them are saying that's when electricity will be on the grid. Not will break even, not will, have a pilot plant on the grid. So that's coming up close. Helion, company that's they're known, they're out there. They don't publish a lot, they don't talk a lot, but they have a contract with Microsoft to provide 50 megawatts of electricity to Microsoft in 2028. Okay, we're 2025 right now. That's 3 years. Their concept, I didn't even include their concept. It's interesting. But they've got a contract with penalties that if they don't produce 50 megawatts and give it to Microsoft in 2028, I don't know what the contract says, but we've read that there are penalties in there. So they think they're going to be ready in 2028. 50 megawatts, not for the power, not for the cities or anything, but at least for data centers, things like that. It's possible. So future work. So what's coming up? Fusion technology demonstrations. The next 3 years, There are going to be a lot of the companies have plans for demonstrations. We're working with a company, Longview Fusion, out of Livermore, who are planning, their next demonstration of technology, mainly technology demonstrations, that they'll then at the end put them all together to form the plant. So that's what's going on the next few years. If you just kind of hang around and watch what's going on, regulatory, NRC has to figure out how they want to regulate fusion. They've already said it's not going to be regulated like fission, thank goodness. That was a lot of companies were lobbying to tell the NRC these aren't fission reactors, these are fusion. So they listened, but they still have to do rulemaking. So if you tried to build one now, there's no regulatory structure that you could use. Then support system, technology development, follow on, a little bit. So a lot of the supply chain, if you get out there, there are companies kind of jockeying for a position to be part of the supply chain for magnets and tritium handling systems and pumps that'll be needed and all these different components, not the machine itself, not the fusion, not the plasma, but all the add-ons. And safety case work will have to be done. That's how do you analyze and tell the NRC or the regulator that these are safe? They have to do that for every fission reactor. So how do you do it for fusion reactors? What are the safety aspects of that? Next slide, I think maybe it. Yep, that is it.
Well, questions? Do we have any questions, Julie?
Come in, Julie.
Hey there, this is Aaron. There is one question in the chat, which is referencing as a question about slide number 26. And the question is, how large is the torus?
How large is what?
The question is, how large is the torus?
Oh, the torus? It's about...
From slide number 26 or 27, yeah.
Slide 26, yeah. Those are roughly 10 meters in diameter. And again, there's no real answer, but I'm taking the Commonwealth Fusion. Commonwealth Fusion is a company that's probably further along than anybody else. Their torus about 10 meters diameter. The spherical tokamak in the UK is smaller. Those are more compact, but a 10 meter radius, a 10 meter diameter is kind of a standard. There's a question here.
Yeah, with the laser fusion machine,
How much energy will be produced or is? Well, these will be full-size reactors. So the first one they want to build is like 400 megawatts electric, but they've got plans then for 1,000 megawatts and 1,600 megawatts. Depends. So the way they get that is just by firing the pellets in faster. So the first one will be like 10 pellets a second, then you do 15 pellets a second, then you get more power. So these are full-size reactors or machines.
So, like this fusion reactor technology works, so will that impact the nuclear reactor business?
The answer is yes. Yeah, and that's a question we discuss that every once in a while. SMRs have not been built yet here in the U.S. and they're starting to be built, but they're still 4 or 5 years off. Fusion is coming in right behind, and yeah, if everything goes as planned, I think fusion reactors will push SMRs out of business, just because of the benefits.
Hey, Fred, could you repeat that question for the people on the line, please?
I'm sorry, good point. The question is, if fusion reactors come on, like I pointed out, the timeline that's on these slides, and SMRs, small modular reactors, nuclear fission reactors are just coming on, and people are looking to build those, if the fusion reactors are successful, will they displace the small modular reactors? And my answer is just because of the benefits of the fusion reactors, if they both work, the answer will be people will want to go with fusion reactors. So don't invest in SMRs.
The U.S. Swing will appreciate that on the website.
Oh, yeah.
They are a fission kind of organization.
No, right now, well, again, I mean, fusion still is a computer model showing it'll work. No one's demonstrated it yet. So SMRs have their place right now.
Any last questions on the chat there, Julie, for Fred?
Yeah,
Aaron's
there's one
taking a
question
look
that
at the
just
questions
came
for
in.
us.
One more question that came in. It says, in the blue zone, how much energy is required to generate? Will it be self-sufficient?
Well, let me think. So the answer, well, several answers, and it depends on the machine type. For instance, I'll use Longview as an example. Longview, if it generates, so the laser energy that hits the hull room, the pellet is 2.2 megajoules. So you have to get 2.2 megajoules out to break even there. If you want to get the lasers powered, now you need a gain of about 15 rather than 1.5. So 15 would be 30. You have to get 30 megajoules out. And then that would power the lasers. You'd probably have to get 40 or 45 megajoules out to power the plant. And so anything above that you could put on the grid. But each plant's going to be a little different. The magnets on a magnetic fusion reactor take a tremendous amount of power. Whole nother discussion on high temperature superconducting magnets, which is another fascinating field. Without that invention a few years ago, magnetic fusion would never have been economically possible. You can't put it. It costs too much energy to have a copper magnet create the fields they need. So something called high temperature superconducting magnets were invented and developed, which allow the power reduction by about 90% to power the magnets. So that's what made magnetic confinement now viable. So it just depends on the designs. And you try to minimize, of course, the amount of power you have to recycle back into the system.
Okay, thank you so much, Fred. Appreciate it.